Okay, so I guess good evening, everyone. I'll start by thanking the organisers for letting me come join this kind of group vacation conference that we're on. So I'm going to talk about some results coming from that 3D survey. For those of you who don't know, that's focused on studying the very boring early type galaxies. That's the one on the left. So the results will be coming from that. I'd like to also thank the previous speakers today because I'm going to be talking mostly about the IMF, and I think you're all feeling kind of familiar with that. Okay, so I'll start by showing a plot where we got the first hint that we might be able to say something about the IMF from the time the Sauron project. And this, I'm showing a comparison here of the mass to light ratio that you get from stellar populations, so running along the x-axis here, against the mass to light ratio you get from the dynamic modeling. And what we found was that there seems to be a saturation of galaxies at the high mass end. So that's the points in the red ellipse there. And the other thing was that we realized that if you don't account for the spread in stellar populations in these objects, then you can get quite misleading mass to light ratios out of it. So I think those are the two things I wanted to take away from this plot, was that there was some kind of saturation where galaxies seemed to get more massive from the dynamics, but they weren't getting more massive from their stellar populations. But we didn't really have enough galaxies here to draw anything too firm, and we couldn't really be sure whether this was a dark matter changing or the IMF. And then a couple of years later, this paper came along, which kind of started the avalanche of work in this field, which quite convincingly showed that indicators of sensitivity to low mass stars were stronger than the traditional model was sort of predicting, and we needed more of those low mass stars in order to account for these absorption features. We've seen a few talks that show that through different features. Okay, and so this was indicating that these galaxies looked heavier because the IMF of these low mass stars, which don't give much light, but they do give you mass. Even more interestingly, this IMF variation seemed to show regular variations with other parameters. So here on the left I'm showing stellar velocity dispersion, and on the right I'm looking at mg over fe, or the abundance ratio. So these trends look quite tight, and so we were curious to know what we could get applying the dynamic modeling that we demonstrated earlier to try to tackle this with Atlas 3D. So the way that we do this, we get the stellar mass to light ratio through a spectral fitting approach. So here I'm showing the small but high value for money Sauron spectrum on the left. We have here metal indicators and age indicators, so it's a small region, but it's quite interesting. And to this we fit basically the smoothest star formation history that the data will permit. And the weights that are applying to each of the bins of age and metallicity are shown there on the right. So this is the kind of star formation history and stellar population modeling approach that we're employing to get the mass to light ratio from the stellar pops. And on the dynamic side, we use this JAM approach, which starts off with a description of the surface brightness, which is shown on the left here, which is coming from this multi-Gaussian expansion approach. And then we apply this Jeans anisotropic modeling technique, which basically makes a prediction of the second velocity moment coming from this light distribution. And one of the key, there's only a few free parameters in this model, the key one here is the mass to light ratio. And this is how we measure our dynamical mass to light ratio. And at the top here I'm showing two examples of data at the top, the best fitting model in the middle, and then sort of a departure from the best fitting model just to show that there's diagnostic power in this process. So we have two measures of the mass, one coming from the stellar pops and the other coming from the stellar dynamics. If we take the ratio of these things and understand everything, then we should basically get the same answer. So the ratio should be 1. And when we did that, we got this plot. So the various panels are showing basically the same thing, but for different assumptions about the dark matter. And basically it didn't matter what we assumed for the dark matter, the fact that these didn't lie in a horizontal line wouldn't go away. And this was interpreted as an excess of mass, in principle coming from the varying IMF. Okay, so now we have a measure of the IMF, which is this alpha parameter that's running on the y-axis here, and that's basically the mismatch parameter between the mass that you determine from dynamics, ratio by the mass that you get, assuming a fixed IMF, in this case saltpeter. Okay, with this measure, we can then see if it relates with other properties. So the color scale on this diagram is showing you this alpha parameter, the IMF mismatch parameter, in colors overlaid on classic indices of H beta and MGFE on the bottom, with a grid of age and metallicity for given alpha abundance elements laid on top. And this is just to give you a feel for how that parameter is varying in this age metallicity space, but staying close to the observations. And from this, you can take away that there's not a simple relationship between the colors on this plot and the directions of age and metallicity indicated by the grid. A more intuitive look at this information is to plot this alpha parameter against age and the separate parameters. And this is what we get when we find it. So these plots have a lot of numbers, but the key ones are the gradient here and correlation significance. And what I take away from this is when you start plotting all these significance correlation numbers, it means that you're kind of struggling to see the correlation by eye. I think someone made a comment earlier of embracing the scatter, but I was kind of keen for the scatter to be a bit less on these plots, but this is how it's working out. There is a lot of scatter in this alpha parameter. Okay, so I'm plotting here against global age in this case. And this is measured in the central aperture, RE/8, which is rather small. With surround we can go out to 1 RE. It didn't actually matter which aperture size I was choosing for these relationships. I'm going to show you the relations are rather similar. So tentative relation here, but very weak and high scatter. Showing this against metallicity, basically it's flat. So no relationship here with IMF and global metallicity. And a tentative correlation here with the abundance ratio. Okay, and if I were to plot here the values from Conrad van Dokkum derived with a pure spectroscopic approach, so fitting these indicators of low mass stars, it doesn't look in too strong an agreement. The relationship here is formally steeper, but in rather good agreement. Okay, I just want to go through some other comparisons here, except the top crash. Okay, and it's in Spanish, so this will be just Thanks. Okay, so this is our relationship with the velocity dispersion, which is one of the tighter relationships that we get from these dynamical measures of the IMF. But there's still a lot of scatter. So from other techniques, this plot was shown in the previous talk, a nice compilation of different approaches here. The red dots correspond to the ones from Atlas 3D, and then the lines and points here are from a variety of techniques actually, some pure spectroscopic, there are lensing results in there. And when I first saw this, I didn't think that the agreement was particularly great. When I thought of the relationship that we got fitting all of the points from Atlas 3D, things were looking rather shallow. And indeed that is the case if you fit for the full sample. But if you're only plotting at the high sigma end, it tends to look steeper. And I think this is nicely illustrated in this plot work by Sabir Bazaki. Here you see the lensing points that they were interested in that particular study as the black points on the far right. And if you were only to consider those, you get a rather steep relation. But when you go to lower sigma, lower velocity dispersion as you can with the Atlas 3D sample, you can see the relationship flattens out and actually everything looks rather consistent. So this is another good consistency check that this relationship seems to hold between different techniques. Okay, so from dynamics, lensing, and stellar populations. There was this interesting, very important, and somewhat sort of annoying paper that showed that we were doing quite well on a number of fronts, but I'll go through those. When we consider what the mass to light ratios we're measuring between different objects, things agree rather well. But for this critical parameter, the ratio of the masses derived with your favorite method, dynamics of populations, ratioed by some traditional number, which is the plot on the right, there wasn't really a good relationship when you plot things measured on the same objects. Right? So this is plotting the same galaxy measured in two different ways. It's basically a scatter plot, and this is, of course, a bit of a problem, but that was nicely dealt with in Maria Lubinova's talk earlier today, and I think I can put a green tick next to this plot, basically saying that if you normalize things in the right way with the same fiducial IMF, then you do get good agreement. So you're introducing a new level of self-consistency here. The IMF is still varying in this plot, as indicated in the colors, but when you deal with the dynamics of the cell population self-consistently, you get agreement. So very, very positive. More perturbing is this. So the plot on the left is what we've seen in a couple of talks today, showing a strong correlation between IMF and local and global metallicity. Actually, there's SDSS points in here which handle kind of a more global perspective type correlation, which doesn't quite stack up with what I put out a year earlier with this kind of flat, noisy relationship when I take my IMF measurements from stellar dynamics and compare them against the stellar populations. Okay, so the left plot is really only the stellar population analysis, the right is combining the stellar dynamics. Okay, so one thing that bothered me was that the stellar populations of these galaxies are varying, spatially varying, right? And this is a global to spatial information type conference, so I have to deal with that. Here I'm just showing some sort of old plots now coming from Harold Kuhn's work from the Sovereign Survey. And you can see this is a kind of a normal galaxy, but it has a young structure in the center, a nice young disk. And you see this in age, it's present in metallicity, not so much in the alpha over Fe, but it's something related to a disk, so some gas in there is forming stars. And this is going to introduce changes, spatial variations in the mass to light ratio. The assumption in the general modeling is that there's a constant mass to light ratio. Okay, so I'm just showing you here profiles of the mass to light ratio from the stars at the top against the age and metallicity. These are just the points measured in each bin. And you can see that there are variations in the mass to light ratio introduced by this young component. And then there's a metallicity gradient, which is also changing the mass to light ratio. None of that is really captured in the current dynamical models. Okay, so what I want to do is try to introduce some improved level of consistency. So not really sure where this would go. I gave it to a master's student who did a fantastic job. His first task was to reproduce the plot from Capillari et al. In a Nature paper, and managed to do that quite nicely. So this is what we had before. This is with constant M over L. And if we introduce the spatial variation in the mass to light ratio and check for this extra consistency, that basically doesn't change much. So I was kind of relieved because it didn't go away. One of the flip sides of this work was that we could then perhaps introduce galaxies that had strong age gradients. So here I'm comparing, on the left we had what we were doing before, where we had to exclude galaxies with strong age variations, which is important if you want to go to different types of objects. On the right, introducing this varying mass to light ratio, things tighten up and become a bit more consistent. Okay, so this is that galaxy again, now peeled apart into different age bins, so you can see the distribution of the stars at different ages. And I'm going to focus here on the young disk at the top, which is actually coincident with a disk in CO, resolved in CO. It's a very nice disk. Very regular. This is some more recent data from Tim Davis. And there are other examples of this. This is another galaxy from Atlas 3D, GC4459. It has a nice dust disk, which you see here in the orange and white colors. And then the sort of blue contours here showing the CO. And this is actually a very regular CO disk with regular rotation. And with this kind of nice rotation curve, you can get measured the enclosed mass as a function of radius. So now we have a way of tracing the circular velocity as a function of radius, the enclosed mass as a function of radius, so we can get the mass to light ratio as a function of radius. This is done through model fit, so I'm just showing you blue contours over the CO data. So that gives us a way to dynamically measure the mass to light ratio as a function of radius. Okay, so this is looking at the overall profile from dynamics. And this is a complicated plot, but at the top, the red points show you the mass to light ratio from the stellar population analysis I talked about. The black points underneath are from this dynamical fit to the CO gas. And then we can ratio these and end up with this mismatch parameter as a function of radius. And this is coming from dynamics. Right? And here's just some other examples of the CO disk. So we have only 7 objects at the moment in the sample. But now we can plot the local alpha, or the local mismatch parameter in measuring these objects, as a function of the localized parameters. And that's what I show here. So different colors are different objects, and we can look to see if they're showing any trends. So this is a function of dispersion. There's not much trend there. Age, there is a trend. Okay, a weak one, but it's sort of there. So there seems to be some relation to this alpha parameter in the local age. Metallicity, interestingly, shows a bit of a trend with the spatially resolved metallicity. And then alpha doesn't show much. Okay, so I'll stick up my conclusions. Basically, so these global trends, when we look globally at the mass to light ratio we get from the dynamics and stellar populations, the IMF variations that you get from this don't seem very strong when you look at the variations in stellar population parameters. And this is a bit inconsistent with what we've seen locally, which may indicate broader problems. These CO disks are a really interesting way of measuring dynamically a local IMF indicator. And so I think there's a lot of scope there for the future. We only have 7 objects at the moment. More data is coming, but watch that space. And when we do that, when we go to the spatially resolved regime, it seems like we get a better consistency with what people get from these pure stellar population analysis. And I'll stop there. Thanks.
Okay, we have for one question I have a generic question. I wanted to ask you also before. I don't understand if this is true. What happens with mergers? If you have mergers and you form bigger galaxies, you change the sigma, but you will not change the angle, right? So
it's a very good question. I think these are at the moment empirical results, so we're reporting what's seen. How this fits into the actual context of the evolution of the systems, I think is where it potentially gets very interesting. And I guess we haven't thought much about what the impacts are and how that stacks up. I think there's been a lot of focus on getting it out of the data in the first place. And I think the next step is indeed that. How does this stack up against a consistent evolution picture?
Okay. Any other question? No? I would be surprised if we can, someone has summarized there in our Twitter, you will you agree with the sentence that is written there? Can you read it?
Sorry.
IMF subsection McDermid, whose data is almost no IMF page, IMF but this is relation. You saw just the opposite of it?
So what we find is that in this global way, when you look at I think you have to understand the weighting that's operating when you compare the dynamical measure of IMF coming from a global fit to the full two-dimensional kinematic map, and the total integrated light that you're using then to calculate the age, metallicity, and so on. Right? So if there are spatial gradients within that, you can quickly muddle things. That's not to say that I'm totally, it's all fixed now and it's all good. I think that would be an overstatement for sure. I think what we need is cross comparisons of different methods, which we're doing, and there are many examples in the literature presented here. What we do see is that the subtle assumptions can make the difference between finding agreement or not. So this IMF business is very delicate, and I think we all have to be careful and conscientious and try to compare as much as we can, as best as we can. For me, the important thing is to find a dynamical tracer that is local. That is not easy. It's hard to do that with the stellar dynamics, which is kind of a global thing.
I think it's a great question. Okay, so let's start training.